Okay, thank you everybody for coming for another Centro seminar today. We have the honor of having João here with us. João started early in his love of mathematics, did math Olympiads, went on to have a PhD to get a PhD at Princeton, being co-advised by Amit Singer and Emmanuel Abe. After that, he did 2 postdocs at Duke and UT Austin before getting here, and now we're honored to have him as one of our researchers. And today, luckily, we'll learn something about learning laws of datasets. João.
And thank you, Paulo, for presenting me, and thank you for the invitation to talk here at Centro. Today, I'll be talking about learning laws of datasets. So we'll be learning a little bit about learning laws of datasets. So this is a project that I started at Duke University, and the idea was, so the way my supervisor at the time sold me the idea was that imagine you were Kepler, you were Newton, and you saw the data from Kepler from imagine you give the data from Kepler to a machine, can it find the gravitation law? Something like that. The idea that finding the laws from the data, and that's a little bit what we're going to be talking today. So how are these laws in nature normally discovered? Or how have they have been, how did they have been discovered this until now? Most of these laws are discovered by performing experiments and getting the data, and then from this data they kind of feed a model to the data, and then they check, okay, this model makes sense, so this should be the law that governs this data. But so nowadays there's more and more data that we're getting, and there's complicated laws that model the data, and it's not so clear how to feed a model to the data, and there's a need to start automating some of these processes. And the goal of this project was to create an AI assistant that helps learning these equations that govern the data. And so what are these equations? A lot of times these equations are given by difference equations. So ordinary differential equations govern a lot of processes, partial differential equations, which kind of generalize that, and stochastic differential equations. So partial differential equations model a lot of systems that have different parameters that correlate with each other, and then stochastic differential equations kind of model parameters that have some stochasticity, and also deterministic part where both play a role against each other and model things that look random, but they have some structure on it as well. And so in this talk, I'm going to be focusing on two methods that we developed in this project. One was about learning partial differential equations, and then the second one was for learning latent SDEs. I'll explain the idea of latent SDEs, and feel free to ask questions any time of the talk, and the talk is quite short, so I have time to answer questions that might arise. And so going on the first method, the idea of the method is as follows. So we are given noisy data points of a function. That's what we are given. That's the training data. And this function is the solution to some PDE or some ODE. So here I gave the example of the exponential function. We have noisy samples of an exponential function. And then the ODE we're looking for is the ODE that the exponential function, one of the that the exponential function satisfies is that its derivative is equal to the function itself. And so our idea was, our goal with this neural network is that, okay, we give it these points and it gives us the exponential function, and then it gives us that the first derivative of the function should be equal to the derivative of the function, to the function itself.
If you don't have enough time ordering on these points,
What?
If you don't know which points go to which points, you're not sure.
So the data itself is like, so we know the time and so we know t and y, x and y in this case. So we know so it's just like, okay, if there was no noise, we kind of can fit the exponential. And now the question is, there's a lot of differential equations that the exponential matches. So we have to figure out a way to define this. And that's a good question. Actually, that's a good question of how to define the problem afterwards that I might talk a little bit more after the talk, or after I explain this first method. But so carrying on, we want to find a function and the underlying PDE. So the main idea behind our algorithm is the universal approximation theorem. And this theorem is a theorem that has several versions, but the one we'll be interested about is one that says that neural networks do not only approximate a function well, they can also approximate its derivatives. For people that are familiar, the neural networks also approximate functions well in Sobolev norm. And so so what's going to happen is that if we approximate the function arbitrarily well, and this is like not counting the noise, right? Because there's some noise in there that maybe complicates things. But if there was no noise, our function could approximate the points really well, and also its Sobolev norm. And so because the derivatives would be close, this function would actually be, this neural network that we got would actually be approximately would actually be a solution of the PDE, approximately, right? And so the idea is to train a network to approximate the data and then recover the PDE from the neural network and its derivatives.
To approximate the data, you have to give the network an idea of what possible PDEs you're considering?
Yes, so we're going to do that, yeah. But so first I'm going to explain so training a network to approximate the data is easy, right? We just fit the L2 loss and then minimize that loss on the points that we have, and that's easy, right? So I'm going to focus this next part on going from, suppose we have a function, how do we figure out a PDE on that function, if that function solves a PDE? So what happens is that most PDEs that people use in practice, and I don't know because it's these are the easiest to solve, or just approximations of real life physical phenomena, but most of them result of linear combinations of simple derivative terms. So a lot of them are linear. It's like some derivative terms minus of the function minus other derivative terms is equal to 0. For instance, the wave equation, the PDEs that are not linear also have like fewer terms. Like this Invisted-Burger's equation, we can say is like a linear combination of two terms. The derivative in time of u, and then u times the derivative in space of u, right? And so normally the PDEs are a linear combination of few terms, and so this is what we're going to be looking for. And so our method requires the user that is applying this method not only to define a dictionary of derivative terms that they think they would appear there. So this is an example. I define my dictionary to be the function u, its second derivative in space, the function times its first derivative in space, the third derivative in space, and the derivative in time. So these are only 5 dictionary terms, but there's a lot of equations that can be modeled with this. So for instance, the it equation is an instance of this PDE, but where the coefficients are 1 that A2 and then I5 is -1. Oh, and I'm going to anticipate one question. So if you have a PDE, you can multiply all these coefficients by a coefficient is still the same law, right? If you have an equation, multiplying all the coefficients by the same number, it still gives you the same loss. So there's this ambiguity that by a scalar, right? So this is going to show up at some point later. But so the heat equation, the Inviscid-Burgers equation, and the KdV equation all can be modeled in this with these 5 dictionary terms, and then this dictionary, you're free to choose whichever dictionary terms you think they would appear. And the good practice for applying this method is to start with fewer dictionary terms and then keep building more dictionary terms if you see what you're getting is not satisfactory. And so now that we have these dictionary terms, we're going to focus on recovering these A's. And so we're going to sample random points in the domain, P1 to the pk. And now if U is a solution to the PDE, then at each pk, this linear combination is 0, right, for all these points we sampled. And so I'm going to put for each pk, I'm going to put this into a matrix. And so what we get is that the A this is exactly the same equation as before, but put into matrix form. And so we get that A is is a null vector for this matrix.
Pk here is in space and time,
yes? Yes. So it's like a function, yes, in space and time, x and t. Yes. That's a good point. Yeah. So pk sample points on the domain that includes both space and time, and then you sample these points. And they don't need to be the sample points you had from the function. It can be any sample points you have on the domain. And so this is what I already said, that this vector A is on the null space of this mu. And so in matrix form, it means that this A is a singular vector is in the null space of this matrix. So a way to find the null space vector is a singular vector with singular value 0. And to find this singular vector, we're going to actually find the smallest singular value, the singular vector that is associated with the smallest singular value of this matrix. And we do have to train these neural networks. We have to put this in a loss way so we can optimize. And the way we make these into a loss is actually using the min-max principle, that the smallest eigen singular value is the minimum over this, where A has norm 1. So
I ask a question. So where is neural network in this framework?
oh, so it's going.
What you explained here, you don't need a neural network. Yes?
Exactly. So we're going to fit. So I might explain this soon. So I'm going to explain now how we train the neural network. So we're going to fit this neural network U to the data. And this is the first loss. It's just a L2 loss to the data. Assuming like the noise is Gaussian, this is like one of the best things to do. And then we're also going to, at the same time, we're going to learn this coefficient A from this neural network that we're feeding. And so we have 2 losses already, right? And so we're going to minimize these 2 losses at the same time. So at the same time that we're...
The word you use,
Loss. Loss. It's like, it's a training loss. Like we have these losses, and then we put this on your favorite like neural network trainer program, like we use PyTorch, for instance, and then you minimize this over theta. And you let it run. You use an optimizer, and then...
What is your data in that case?
The data is the function value, noisy function values. Of the...
Oh, then I have a question. So you had there U and 3 derivatives of X.
Yes.
Is it a part of the data?
The derivatives, no. So the derivatives you take from the neural network.
Okay, so you try to make neural network which fits the data. You take third derivative from the neural network, and you find A optimizing this.
Exactly. And so this way to take derivatives of the neural network, so the first thing they did was find a way to calculate gradients easy without people calculating this, without using backpropagation, but now it's also implemented in a lot of these programs, auto-differentiation, which is this way of using backpropagation to actually compute higher order derivatives as well. And so this is also not hard to do in this neural network program. So actually using the neural network, you can just take derivatives of it as well using auto-differentiation. This idea of you do this and then you create a graph of the operations you did, and then it goes back to this graph and does back propagation with this bigger graph with the calculated derivatives. And so we also have a third part of the loss, which is going back on these functions. We notice that we can have a lot of dictionary terms, but the number of terms that actually appear in the PDE normally are quite small. They 2 or 3, most were 2 or 3, right? And so we believe that the A is a sparse vector. And so to enforce that A is a sparse vector, we also have a sparsity constraint. We minimize the rank 1 norm of A, weighted by some constant, so that it enforces that the norm of A goes to the A is sparse. And now we join these three. So we tried different ideas. We saw that this was the best way to this loss written like this was the best way to model the loss. A little bit why we're explaining a little bit the reason why we're multiplying this part here instead of adding it with the lambda is that, so in the beginning, the neural network that we have is not related with the data at all. So any law that is trying to learn is going to be garbage because its derivatives are not related with the actual derivatives of the function at all. So we noticed by using the loss, and this is an empirical thing, it's something we tried with trial and error, and this one seemed to work well. By doing this, it would first try to fit the data in the function to the data, and only then, when it had already, the function was closer to the data, it started to learn or to better learn this PDE, basically the coefficient vector A. And so this worked well, and so we minimize this. We enforce that, so we have to enforce that the norm of A is 1, because if you let A to be anything, the best solution is just A to be 0, and you're not going to get anything. And so we force the norm of A to be 1, and we enforce this by projecting the gradient. So you project the gradient into the sphere. So you think of this as like some Riemannian optimization. You project the gradient of over A into the sphere, into the tangent space in the sphere, and then, but this still can get you like a little bit out of the sphere. So we also rescale A after every optimization step. What ends up happening is that the norm of A is always 1 during the optimization. And this rescaling doesn't affect the other parameters for optimization a lot. As it could, but because we're projecting and it's just doing, the rescaling is very small. But it's good to keep doing it all the time because it's easy to do the projection. And it's something that we should do. And so, and by doing this, we got something that we were not expecting, is that if we think, I'm sorry that this is not very well formatted, but so if we think about this term, it's okay, let me see if I can. Okay, if you think about this term here, and you optimize it in terms of theta, theta are the parameters for the neural network that is feeding the data. It means that it's also trying to fit the function itself is also trying to be a solution to the differential equation that it's learning. So at the same time, this is like regularizing the function, making it smoother by making it a solution to the actual PDE that it's learning. So this was some effect that we didn't think it would happen. And so the learned function is actually very smooth. It's not like, it doesn't have spikes, even though the function values can be quite noisy, but the function learned is quite smooth. And so let me give some results here. I like this image a lot. So we did this for the Helmholtz equation. So the data itself has two dimensional. So the domain is two-dimensional. It's just the square, 0, 1. And then the Helmholtz equation is given by this. This is a solution to the Helmholtz equation. There's more than one in this domain. It depends on boundary equations. This one, I thought it looked nice. It's like a cosine times a sine or something like that. There's some wave function. And then we chose a derivative dictionary with 7 terms. So the 7 terms we use are the ones that I wrote over there. There's some linear terms, some terms that are not linear. And now the actual solution is the one I highlighted in orange. And then we feed this to the neural network. So we feed these noisy points here. So this is the actual solution. And we feed this to the neural network. And it gave us this. So this, it looks almost like the original. If you look quite well, you see that there's some mismatch in color, but they're very, very small. It's very smooth as well, and the coefficient error is also very small. It's like it actually learned these things, this law, up to error that is of this order. And so,
Actually not so small.
I mean, it's
4%.
okay.
4%.
Yes, I mean, given the noise in the data, I think it's not.
No, it's quite good.
Yeah, and so I'm going to. This is it for this method. I'm going to be talking about SDE next. Are there any questions about this method or?
What happens if you give to this solution which is not in your dictionary, or the PDE which is not in your dictionary? It will just give some.
It will try to learn the next best thing to it. Like an example, for instance, is suppose you have an equation with 2 waves. It's like the UTT equals UXX, right? You don't put UTT, you just put one of the UTs. What used to learn, we tried that, was just one wave, so the solution is normally like 2 fronts equations for that PDE. It will learn one of the fronts and forget about the other. So it will try to learn some like kind of PDE that is similar to some of the things that are appearing there.
Did you try to add in your dictionary higher order terms?
In this,
So having third derivatives, and okay, there is no actually term of mixed derivative xy. Yes, would it just learn, I know, by mistake, one of those coefficients? Yes?
So if you add a lot of terms, you can get things like this. So this is actually a good question because it comes to, there's a problem with this method that comes a little bit with your reasoning. So suppose I also added, so let me think of a term.
I don't have a reason, it was just a curiosity.
Yeah, but suppose I added the term uxxy, right? So one law of this is uxx plus uyy plus u equals 0, right? Now if I take derivatives of all of these in terms of y, I get, no, in terms of x,
Why?
y. Yes, you're going to get uxx. I didn't choose a good example.
No, it's a good example.
No, but so
uxxy plus u3y.
yeah.
Y.
But there's no u3y in there. So what I wanted to show is that if you have enough terms, you can get more than one PDE that is governed by that.
That was the idea of my question. Yes. So because if you add more higher order terms, then necessarily another law will appear. Yes. What it will actually learn in that case?
So it will learn one of them. So it can't.
Maybe a variant of that. It says if you put in the dictionary one more term, uxx 3 times, will it come up with 0 for that column?
Oh, so it's like.
Yeah, just experiment in the dictionary, add a third order term, uxx. Then would your result would give 0 for that coefficient?
I don't. Yeah, I think so, but it depends on because if you add more order terms, it can start to be closer to like a solution of some other PDE, right? And so how to solve this is not clear to me. One idea is that this is a way to like match the data. So one thing you can do is start by smaller order terms and then go up, right? And then other thing, you can try to put more A's. So try to learn more laws and try to minimize that. And that's another way to try to solve this. We didn't try to think too much about it. It's a nice thing to think about future projects, especially if there's like some particular data set that might be challenging. Could be a good target for it. I think it's a good thing to think about in the future. Like what happens if...
For PDEs, there are not so many. With a few, 2, 3, 4 PDEs, we describe most of physics. But for ODEs, then it's wilderness. So how can you still expect to do that for ODEs? Also, same approach? Or?
So ODEs, it would be. So this also works for ODEs, like the exponential example I gave. Yeah, I'll be.
The equation can be very wide.
Exactly, like with derivatives.
While PDEs are relatively tame in some sense.
No, but like ODEs normally, so sometimes they also have fewer terms, right? So it depends on how much terms it would have. But if it would be, so that takes me also to another good question: is that what if the relationship is not linear? It's like it's some combination, weird combination of the terms. That's another question we want to think about. The problem is that if you want to learn something like that, you have to enforce that it doesn't learn something that's 0 equals 0. Which it's hard to enforce not to learn that if there are linear coefficients, but if you add some function, you can learn the function that sends everything to 0, and then you're not learning nothing. So it's also a good question is like try to learn this with a function that does not go to 0. Does this answer your question in some way? Okay. We can maybe discuss a little bit afterwards.
Couldn't you, in your loss function, add some kind of term to give more priority to lower degree PDEs in case you didn't want to, for example, hit the higher order? So basically some regularization style mechanic in your loss function.
I mean, maybe you could. I mean, it's just you could weigh A in a different way, so you could do that. In principle, you could. If we haven't tried that also, but it's a good idea to try, I think. Yeah.
You know, in your case, what's the factor for the derivative dictionary that you get in your
The what?
See, the answer here of this derivative dictionary that you have in orange is 110, 01, 000, right? In your case, do you know from the neural network what was the vector that it got?
It was a vector that was close to this one up to this error that I put in
The error is on the vector?
Yes.
Oh, I see.
Yeah. Now I'm not sure if the error was like L1 or L2. but
But how much did it depend on the architecture of the neural network?
it depended a little bit. For this neural network, actually, I do not recall what was the architecture used, but it was like, so for this thing, because the function was smooth, it's like smooth activation functions, like some, it was like some soft ReLU with and like full layer networks. So the function itself, so this is actually like, the function itself is the number of parameters are not big because the size of the data is like two-dimensional. So you don't need a very big, a lot of parameters to model this function. And we didn't use anything like conventional neural networks or anything. It was just like some full layer networks with soft ReLUs or something like that. Yeah, it depended on it. We couldn't use things that were not smooth for this thing, of course. And
I mean, how do you know it's two-dimensional?
oh, because the data itself is like two-dimensional, right? You can have hidden layers that are more dimensional, but the data itself is three-dimensional, really, because it's no, the neural network is two-dimensional because it goes from the domain, which is a square, right, is 2D, to the reals. So the function is like that. So you can have maybe more, the hidden layers can have more dimensions, but the input is two-dimensional and the output is one-dimensional.
You have points like values you don't know how to format them. You have to assume something to get two dimensions. You cannot, it's not contained in the data.
So our data is already two-dimensional in this assumption. Like, but so there's the next project is a little bit maybe similar to what you think, because in this project we actually assume the data itself is like a small dimensional, like a PDE or something, and then the actual data itself is the PDE. The next example is going to be an example where the data itself can live in a weird domain, but then there's a transformation that transforms it to a smaller domain that actually is followed by SDE. So maybe, yeah. But the next one is for stochastic differential equations, which can be thought of as like generalizations of ODEs. So maybe it can also help understand some things. But okay, any more questions about the PDE work? Okay, I'll keep going on. What time is it?
So if
Okay.
about general questions about PDE, so then there are plenty of PDEs where you have solutions only in weak form. Yes, so with the shock fronts and so on. Then, of course, the approach which you tell might be not really good, yes, because kind of derivative doesn't exist. For the
Exactly.
function, yes?
Yeah.
Did you try it? Because in some sense, you know, sometimes with this neural networks, it just works by magic. Yes.
Exactly.
After
Exactly.
that,
Yeah.
You need to think by the whole institute. Why does it work? Yes.
Exactly. No, it's not by magic. It's like by trial and error a lot of times. It's but yeah, we haven't tried the chalk or like PDEs that are more complicated. We tried this
No, but
like
you
the one.
actually included one of them. U sub t plus u x is equal to 0. If I'm
Oh.
not mistaken, it is.
It can have chalks, right? We didn't look at parts where it had chalks. It's
I
just
didn't look on the past. Then it's very easy for you, you know. Next work.
How do you get the, what is the equation for the neural network, and how do you choose it?
what? So
What is the equation for the neural net? What is the architecture, and how do you decide which one you take?
so the architecture is like it's so it's like you have, in this case you have like two inputs, right?
Okay, any one of them, or just this
What?
one? In this case,
See-
in this case, you mean?
Yeah. So in this case it's like two inputs.
But what is this case? Is the first line?
First line.
Yeah.
That's
okay.
the equation that.
Diagonal one. Okay, sorry. So, n mod. Okay.
Yes. So Helmholtz equation is the PDE that we're looking for, and this is a solution for it. And then the neural network, the architecture that we used is one with like so I'm not sure because it's been some time, but I think it's like one with like you go to a full layer network, then there's some activation function phi, and then another full layer network, and there's a bunch of this. I don't know. I don't think we have a lot. It's like it's more wider and less deep. I think it's because of like the gradient to not be too big, to not lose a lot of properties. So it's like wider and less big. I think it's 3 deep and wide is a lot. It's like 100 or something like that. And so you make some like this, and in each part you do a interwise activation function, which it's like a small the activation function looks like this. And then in the end, it gives you a value, which is the function value. And this is the neural network itself. And now you can take derivatives of the neural network with respect to this function. Because this is a function, you can actually take the derivatives of this function. And that's how you build all these derivative terms that you use in the loss. Did this answer the question?
No, but that's my fault.
Okay, I'm sorry. We can maybe discuss afterwards. Or, yeah.
Another question. So you can take, did you try to take a question where solution is sensitive to the initial data? So, okay, I'm speaking about time dependent, but of course you can speak, construct a similar for not time dependent. So when you slightly change, say, boundary condition, then your solution changes a lot. And pictures are not so nice and smooth, but have some, I don't know, solution of them. The original solution, yes, the true solution has some, I don't know, fractal structures inside.
Okay,
yes.
yeah.
Yet, did you try or not? Because there are two possibilities. Either you can learn averaged equation, yes, because sometimes you have average models for this, or you can learn original equation. And this is two different possibilities, actually.
Yeah, that's a good question. We should like maybe try to figure out some of these models and try to learn. Yeah, because these are all questions
very
like
easy equations, but it's very complicated equation.
exactly. It's we haven't tried anything so complicated or something. We just noticed that for some of the most so we mostly use the synthetic data. I'm not sure if you used any real data, but I think mostly was synthetic, and with neural PDEs that worked well. And
The correspondence between artificial and natural data is known. I mean, can you rely on some theorems or stock of data to be happier doing one when you don't intercept the other?
I don't know. I didn't understand the question too well. Do you say
So
like?
You say that you did not study the case when the data is natural, but do you know what do you have an intuition of what would happen? I mean, why do you think that like
I mean,
important case? So, what allows you to do that, to not look at natural data? Because you know that it's always good or often good or...
oh no, so we didn't find a lot of data sets that had this PDE structure behind them, and at the time we didn't find a good data set to try it on. And then if you want to apply it in real data, it depends on the actual noise that the data has, and I'm not sure what kind of like I don't know. It depends on the data set. We might have actually. I'm trying to remember, because this paper is a little bit old, if we applied to real data set or not. I think we didn't. But it will, like, if you have to apply it on data, it will give a little bit more work for sure to make it work. But But it's a customizable model because you can define all these dictionaries and you can take the loss. So you can change all these hyperparameters that you use to train, and then you can check also if the function actually is feeding the data and all these kinds of things. Let me, because I'm short on time, let me go over I have two methods, which is supposed to be half and half of the time. Now it's going to be a little bit less for this one. But so this is a different problem. And this is about learning latent SDEs. And I think the best example to explain this method is with this example on the left and what it gives on the right. So the input of this data of this neural network is a video of some process, of high-dimensional process that is governed by a stochastic differential equation. So in this case, I have a video, images of a ball moving in a 2D motion, where the 2D motion itself, it follows an Uhlenbeck process. It's like a stochastic differential equation. It's like a Brownian motion, but it keeps getting, like, it has incentive to go to the center. And so the idea is, so what I told the neural network, I gave it the video, and I told it there's a latent SDE. So in this case, latent meaning that there's a stochastic differential equation governing the data, but it's not the actual, so the data itself is just images, is pixels, right? But there's an underlying SDE which has dimension 2. So I tell it the dimension. And can you find the actual stochastic differential equation? It found the stochastic differential equation. If you look on the right, so the blue are the actual centers of the ball as time passes. Orange are the ones estimated by our neural network. And so you can see that it fits it really well. And then it also learns the drift coefficients. It's not the best. The drift coefficients are not learned very well, but it's also because stochastic differential equations can, to learn the drift coefficient, sometimes it's hard. And so that's why it didn't learn it that well. Sometimes you need a lot of data to learn well the different drift coefficient. But, and so, let me explain how we solve this problem. A little bit first on what are SDEs. So stochastic differential equations are, you can think of it as a generalization of ordinary differential equations, where you have a drift coefficient which corresponds to the deterministic part of the differential equation, and then this diffusion coefficient which has stochasticity. So the bigger the diffusion coefficient, the more it jiggles. Like, you can think of this as volatility in the action in the stocks market, and the drift coefficient is just measuring the actual, like, the actually different. No, the drift coefficient measures the tendency of what's going, yeah, like the average case, exactly. And so if there was no diffusion coefficient, this would just be an ODE. And so explaining with the notation with SDEs, what we observe is this xt, which is a function of zt. We don't see zt. The only thing we see is xt. And we know that zt follows some SDE with drift mu and some diffusion sigma, diffusion coefficient sigma. And so we don't know f, mu, and sigma, and that's what we want to estimate. So this is like this looks like a very hard inverse problem. But so what we're going to, so the first part we're going to think about is one that comes from Ito's lemma. So suppose you have a solution of an SDE. Then if you apply a function to every point of the solution to SDE, the values that you get are also a solution to another SDE. And the reason, and you actually can, Ito's lemma gives a formula for this mu tilde and sigma tilde in terms of G, mu, and sigma. But so what happens is that because this is true, so suppose you have this model which is xt, f, mu, and sigma. I'm going to get another model which can just as well explain the data, where f tilde is equal to f after g, so f is equal to f tilde applied after g, so f is f tilde g inverse, and then this yt, this mu tilde and sigma tilde is just the mu and tilde you get by transforming with g. So if you apply a one-to-one transformation to the latent space, you still get, and because you don't observe the latent space, you don't know nothing about the latent space, you still get another representation that can be a viable representation of the latent space. And so there's this one-to-one ambiguity that we have to solve for. And we found a nice way to solve for this. So if suppose that the underlying model is like this, and now under some conditions on mu and sigma, you can actually choose this g, this function, this one-to-one transformation g, such that this the drift coefficient is the identity at all points. So this condition it requires that sigma has some parameterization, but it's a parameterization that makes sense in some cases, and so so the idea is that under these conditions that make sense, you don't need to learn the diffusion coefficient. You can assume it's the identity. So you're just going to learn this function f tilde and this term mu tilde. And now, if you actually have some information about the latent space, you can just learn this one, and then if you can try to find this one-to-one transformation that gets you to the transformation to the information of latent space you think you know about. And so now that you only need to learn about f tilde and mu tilde, we're going to use variational autoencoder to learn this. So let me explain. For the people that are not familiar with variational autoencoders, it took me also a long time to understand it. But so an autoencoder is like so autoencoder is like this. So it takes an input which is I-dimensional. So this is a dimensionality reduction technique. You take an input that is I-dimensional, you make it smaller into a low dimensional latent space. It's like the space in the, so it's the space of variables that are lower dimensional that describe your data. And then you go here and you want this E tilde to be close to I.
Do you know what the latent space is?
So normally no, but like imagine you have some, so this is idea. So imagine you want to you have some data and you just want to reduce the dimensionality.
In what sense? What do you accept?
Like imagine you have images of people and you just want to actually have like this information, like this smaller information, like just things that like age or something that can get you back to the photos afterwards. So the way you can like try to learn these things is you mount a neural network like this, and now the inputs you take the images, the output are the images you output over this neural network. You try to match the output, minimize the error between the output and the images itself. And now this kind of gives you like this way by looking at this latent space, you can actually have a smaller representation of the images.
You do that once or you iterate?
You train and then you minimize over, like you do optimization and then you do gradient descent until you find something that you're happy with. And you use all these tricks like stochastic gradient descent and like optimizers, accelerated optimizers, and you train it and you'll get something that you're happy with. So this is an autoencoder. A variational autoencoder is something similar, but like in this latent space, there's like this probability distribution. And you kind of like minimize this KL divergence, like you minimize the KL the KL divergence between this probability distribution and what you get in the end. In another way to think about it is like in the latent space, you not only get the latent representation, you also get this kind of variance that tells you how sure you are of this latent representation. And now you can try to minimize these as well. Like variational autoencoders are better when the data is noisy. So like you want to it also removes the noise in the process or something like that. But so this also explain that I used this variational autoencoder. And so the latent data itself is a latent ZT. And then the next step in this, so we have a time series of these images, right? And so ZT is the latent variable and the latent variable in the next step. So, and the input for this autoencoder is like pairs of consecutive images. And now,
one is a full image and the other one is a reduced image. What is a pair?
no, so this pair is like pair of consecutive. Oh, sorry, I'm going the wrong direction. So pairs of like, so you see the image and the image in the next step.
And
So
then you take each image once,
so you take each pair image once. So you take like x0, x1, x1, x2.
you cover twice.
Exactly. And now this is your like input for the VAE, and then the latent space is some ZT, which is it follows the SDE. And now the SDE is trained so that XT is approximately a function of ZT. This is what we get. XT plus delta also uses the same F. And now ZT plus delta T minus ZT is approximately a Gaussian, because that's with the mean mu ZT times delta T and variance delta T IN. So this is approximating the SDE map, XDE thing. And this is like the variational. So variational autoencoders have two parts: the encoder, which is this part here, and the decoder, which is this part here. And so the encoder has some probability distribution, which is given by this. So it has some. It's given by probability distribution, which we factorize in this way, and then the decoder is factorized also in this way. And now with the decoder and encoder factorized in this way, we minimize this loss. So this is like the loss for variational autoencoders. This is the loss that at the same time tries to minimize the KL divergence between the decoder, what the decoder learns, and the encoder and the prior distribution of the encoder. And the other one is tries to maximize the likelihood of this P over the decoder. But both these terms like this you can calculate them, but actually computationally, but this last term in the bottom is the one that you use for calculating the loss. there's also a part of this result that that we can actually recover as the number of, as you get more and more data, this VAE is going to allow you to actually learn this F and this mu and this, so the F, which is the function from latent space to observed space, to the images you see, and then this mu is the drift coefficient, and then there's this this term p gamma, which is the prior that the latent space has. And so you are able to learn all of this up to this isometry Q, which is a matrix. It's just the isometry is just QZ plus B, the function, and so you can only learn up to this because if you have a SDE and with isotropic diffusion coefficient, it means that the diffusion coefficient is the identity in every part. If you apply isometry to it, you still have SDE with isotropic coefficient. Does this make sense? So you can only learn up to this Q.
But when you have two successive images, you actually assume that the second one is a small perturbation of the first one, or they jump all the...
In latent space, they are. Like, so think of it this way. So suppose you know the function, right? If you know how to go from the picture of the circle back to the center, you say that the function from the picture to the center is some function you want to model plus some noise, and that was one of the parts. And then from that to the next step in the latent space, it's so the latent space is also the same thing. So from xt to zt is this, xt plus delta t plus zt plus delta t is this, and then the difference between these two is small. And that's what's modeled more or less by this p that I showed before. It's like we factorize the probability distribution.
The type of evolution that you have in a movie, for instance?
Yes, so
It's not like a random collection of big pictures. It's more like a movie where...
yes, so SDEs have time dependent, right? So it's the data itself, we assume it's like a movie. It's like a time series, right? And so we always look at...
It's continuous. I mean, everything is a time series, but it's relatively regular in this direction.
Regular, more or less. It's regular up to like SDEs are like discontinuous, right? So there's that part. But besides that, it's kind of regular. So another question is, what happens if you have gaps between the time series or something? How do you model that? It's something we considered, and but we didn't think about it too much. But something you can try to do. But so because I'm a little bit late, let me just show the results of what we get. So this is one of the data sets, the first one I showed you, and so what I'm showing here on top is the original data. On the bottom is the latent space that it learns. And it's just a two-dimensional latent space, and it's still learning the circles quite well. And it also learns the other things I told you about drift coefficient or something, but showing this would be more complicated. But so this was one of the data sets we considered. And then the other one is using optimal transport images. So these are images that come from doing an optimal transport between an image of a cat, and I think it's an image of a duck, if I'm not mistaken. And so you can do these Weierstrass barycenters, and like you can basically do a map that goes from is 0 in the you can do a space of images which when it's 0 is just the cat, when it's 1 is the duck, and now this between 0 and 1 you have this one-dimensional process that you can put an SDE on it. And so we trained, this was the original data, an SDE moving on these various, so it was a different kind of data set to not have something moving on a video of something moving is something more complicated, because it's even like calculating these things, these Wasserstein varicentres sometimes take some time, but still our algorithm was able to find the SDE, and in this kind of data set. We tried with more balls, it still worked. And we tried mixing a ball with this data set, and it still worked well. And there's also like some part of it which is like the color gets faded in some parts, and it still worked well to learn where the ball was and the image that was underlying. We added noise and still worked well. So this is the original data. This is the data we fed to the neural network, and this is what we got. So you can see that there's a cat hiding behind all this noise, and it's actually recovering this cat. And we tried with the real data set. So someone recorded an atom moving in with a lot of noise, moving with some captured an atom or a molecule moving in some with some electron microscope. And so we used that as a data set. I learned that the atom is actually moving with a Brownian motion, and we got the centers of the atom itself, which is actually like estimating the centers seems an easier problem than it actually was, and we actually got a way to estimate these centers. And there are some other things that we considered that I'm going to skip through. So different time sampling frequency, then SDEs with time dependency, where mu, I didn't talk about this, but sometimes mu and sigma, the diffusion coefficient and the drift coefficient, depend on time. Our results also work with that. There's the problem of determining the latent dimension, where here there's two things that I suggest to do. One of them is try lowering dimensions and increase the dimensions and see what you're getting, and see when you get something that you like. And then another idea is to try to, instead of learning a drift coefficient, try to learn a covariance, a diagonal covariance, and then put a sparsity constraint on the drift on the diagonal. So this is going to push the LU norm constraint on the diagonal terms of the covariance. This is going to push some of these covariance terms to go to 0, and maybe you'll get a nicer thing. Maybe it will give you the right latent dimension. And then the next thing, other thing we do is that, so to see how good we're doing, we compared the error that we got from our method with Kramer-Rao lower bounds that we got for this problem. So what any estimator could do for this kind of problem. So here we want to estimate a full function. So we want to estimate the drift. Instead of estimating the drift function, which we don't know, we assume, okay, we just want to consider the problem of estimating the drift function plus some constant. So we assume we know the drift function, we just don't know the constant. This is clearly a lower bound for the error of just learning all the drift coefficient, because what we want to learn is just a constant. And so this is the Kramer-Rao lower bound for our problem. It's a crude lower bound. We did get the error scaling a little bit like the Kramer-Rao lower bound. So that was nice. And this was the main collaborators on this was Ali. Ali Hassan was a PhD student that did most of the programming and training these neural networks. And then Sina is his PhD advisor, and Vaid was my supervisor at Duke University at the time. And the codes for these two methods are here, and the papers are here. Okay.
Thank you very much. We're a little bit late on time, but does anyone have any questions? One, maybe final question. Nope. Since we asked everything we had. Thank you.